So, today I will continue my lectures on metals in biology. In my last lecture we have discussed about the biologically important elements, and as I have said that 99% of human body is comprised of 11 elements, and we also discussed biologically essential and non-essential elements. We also discussed in my last lecture that why certain elements are selected out of so many elements present in the periodic table. There are some guiding principles which nature has followed in order to select certain elements for their function and role. So, some of this we have already discussed, that their abundance, their basic fitness, efficiency, evolutionary adaptation to realize critically required specificity, solubility under physiological condition. And what we have noted that lighter elements are abundant, therefore utilized more. All the elements appreciably abundant in human body are also abundant in sea water, which suggests that our family tree is rooted in the sea. We have shown in my last lecture that certain elements are either concentrated or diluted in human body. For example, that sodium which is diluted, while several such elements like iron, nickel, copper, zinc, molybdenum, they are concentrated in our body by many thousand folds. And we also discuss that how these elements are transported across the cell membrane. There can be passive or active transport, and there can also be ion specific channels through which ion can transport across the membrane. We have also discussed that how the metal ion which are less abundant can also be increase their concentration in the body. For example, how iron is getting inside the cell by using enterobactin. We have discussed this in details in my last lecture. Now, what role does the metal ions play? The metal ion is present in the active site of the metalloenzymes, and they have either functional role and or structural role. However, metalloenzymes without metal ions are simply inactive. So, you can see that how metal ion is important. Now, this being so, they have to have a concentration range, without that it also can act as a poison. For example, I have shown here that effect of copper ions on the height of oat seedlings. As you can see, as the concentration of copper ion increases, then the length of the seedlings increases, and after that it also decreases. So, it depends on doses, individual health and the way of administration. What we learned is that metal ion concentrations must be maintained within certain range inside the cell. So, schematically it has been shown over here, state of the health and intake of element has been plotted. As you can see that for a healthy condition you need to have a concentration level when the health would be very good. However, if you have either excess concentration or deficiency, both are bad, and both of this creates variety of disease for our body. And if the concentration increases to a value where it is highly toxic, it will causes a death. Similarly, without that element also the system would die. So, this is the physiological effect. So, we do not need too much, not too less, we have to maintain a healthy condition. So, metal ion concentration must be maintained within certain ranges in the cell. Now, here is a plot with non-essential elements, those elements whose presence are not essential for our body. If you see, so there is a tolerance level, and once that tolerance region crossed, then there will be a disease and eventually it will causes death. I have shown here a table where the symptoms of elemental deficiency are shown. For example, calcium, retarded skeletal growth, magnesium, muscle cramps, iron anemia, zinc, stunt growth, skin damage, copper, liver disorder, molybdenum, retarded cellular growth, cobalt, pernicious anemia, nickel depressed growth, chromium diabetic symptoms, silicon skeletal growth disorder, fluorine dental disorder, iodine thyroid disorder, selenium cardiac muscular weakness, arsenic impaired growth, of course, in animals. So, what is needed? That we need to have this element to a concentration which is necessary for our growth. If we do not take those foods carrying, for example, here I have shown that calcium supplements, there are lots of food items is shown over here including milk. If we do not take enough food having calcium, then we have to take medicines. Now, the effect of metal deficiency, particularly calcium deficiency, is shown over here. So, you will have, because calcium forms these bones. So, you have joint pains, teeth discoloration, poor appetite and lots of other things. Copper, if you have excess, then it causes Wilson disease, and Wilson disease creates lots of problem in our body, particularly liver. You see enlarged liver, jaundice, acute hepatitis, lots of disease it creates, arthritis, rickets, and in central nervous system also it affects, and there are also cardiac problem, renal problem. So, Wilson disease is very bad for us, and it is basically due to the copper ion if it is present in excess. So, some of these symptoms are shown over here: cirrhosis, kidney damage, liver cancer, liver failure, nervous system problem, and it can causes death. So, be careful with that. Copper deficiency also creates Menkes disease, and Menkes disease also I am not going to discuss all in details, and it creates problem in brain, skin and hair. Low copper contents creates the lot of problem, bones, kidney, and dietary problem also. Iron deficiency causes an anemia. You all are familiar with anemia. So, we need to have proper iron concentrations in our body that we take from the diet. So, the foods which are rich in iron are shown over here: meat, egg and lots of vegetables, and if we do not have sufficient iron concentration in our body, then you have to have medicines to supplement the iron deficiency, and some of these medicines are shown over here, which doctors usually prescribe. Iodine deficiency. Failure to have adequate iodine leads to insufficient production of thyroid hormones, which I have shown earlier, resulting in disease known collectively as iodine deficiency disease IDD, such as goiter, mental retardation, physical sluggishness, growth retardation, and nearly 1/3 of this earth population, including us, live in an area of iodine deficiency. And as you can see that this thyroid gland, which is present in the neck as I have shown, and if iodine is lacking, then what would happen? The thyroid gland will swell, causing goiter and other disease as shown earlier. Fluoride, another important element. So, if you have deficiency, then you have tooth cavities, tooth decay and loss of teeth. And if you have excess, fluoride causes dental fluorosis. You see, there are all depositions. So, deficiency also bad and excess also bad. So, you need to have proper concentration for our healthy life. Now, coming back to the metal ions, say for example, non-redox active metal ions. Say sodium potassiums, what they do? They are actually biological messenger, charge carrier, osmotic and electrochemical gradients, nerve function, they are responsible for that. Magnesium, calcium, lots of enzyme like enzyme activators, structure promoter, they are also Lewis acids. We will see some of this activity. Magnesium 2 plus, calcium 2 plus, you know that chlorophyll, photosynthesis. Zinc, mainly found in hydrolytic enzymes, structural promoter, substrate binder, Lewis acid, found in large number of enzymatic systems such as carbonic anhydrase, carboxypeptidase, etc. Now, why zinc is being selected in the enzymatic activity? Zinc is Zn2 plus is a typical Lewis acid. However, if you talk about Lewis acidity, then copper 2 plus is a better Lewis acid than zinc 2 plus, but still nature selected zinc rather than copper. Zinc has, however, very stable oxidation state +2, whereas copper has the stable oxidation states of +1 and +2. Of course, +3 is highly oxidizing, so it will not be stable in the biological system. So, for copper enzyme, there is a risk for initiating the redox reaction. So, nature wanted to avoid, because it will be complicated, and that is why zinc is being selected. Also, zinc has several other characteristic property compared to other elements in the periodic table. For example, zinc 2 can easily be 4, 5 or 6 coordinate without a marked preference for 6 coordination. The electronic configuration of zinc 2 is D10, and so there is no ligand field stabilization energy. Kinetically labile, this enables the replacement of water molecules from the zinc coordination pair by a substrate, which can occur very rapidly. Similarly, ligand dissociations also. Zinc is an ion borderline hardness, and thereby it can bind both hard and soft donor atoms like nitrogen, oxygen, sulfur. Zinc 2 plus ion is an exceptionally stable with respect to oxidation and reduction. All these characteristic properties make zinc suitable for this biological catalysis. Let me explain little bit more on one zinc containing enzyme called carbonic anhydrase. What carbonic anhydrase is doing? The carbon dioxide plus water forms bicarbonate plus H plus, which is catalyzed by carbonic anhydrase. Now, what would happen? So, this is the structure of carbonic anhydrase. As you can see that there are 3 histidine and ligated to zinc center, and 1/4 position is ligated with water. This carbonic anhydrase is present in animals, plants and certain microorganisms. However, if you do not use carbonic anhydrase, the same reaction is too slow. K observed is 7 into 10 to the power minus 4 per second, very slow. As you know, our body produces carbon dioxide which have to be released from the body. Thus, this bicarbonate formation, carbon dioxide is a gas. So, bicarbonate formation is very essential, and nature had to design an enzyme carbonic anhydrase which actually speed up this reaction at the order of 10 to the power 7 times, and turnover number for this reaction is 10 to the power 6 per second, a huge turnover number. The mechanism of action of zinc containing enzymes are shown here. So, zinc 2 plus is basically an Lewis acid. Now, water, the pKa is around 14. Now, when it binds with zinc, what would happen? The pKa of this water drastically becomes low, is close to 7. That means, the proton is more acidic, and so then it leads to a deprotonation, just like shown over here, OH minus, because protons are highly acidic. Even a base can polarize and even decreases the pKa of water lower than this, it can be more acidic. So, additional activation by a basic residue to generate an incipient zinc hydroxide. Substrate can replace water and thereby enhancing its nucleophilic attack. So, a pore nucleophile is increasing its nucleophilicity just by coordinating with zinc, and this is what is happening. As you can see this mechanism of its work. So, this is the resting state of this enzyme carbonic anhydrase, 3 histidine ligated with zinc ion, and the 4th position is in water molecule, and as I have said, the proton is acidic. So, it releases proton, and histidine 64 acids in the H plus removal. So, it becomes OH minus, and then carbon dioxide enters, and this negative, there is a nucleophilic attack to carbon, and this forms a intermediate, very unstable intermediate of this type, as you can see, this bicarbonate then be released very easily. Water replace this bicarbonate and it convert again the enzyme. So, this is the way it works, and then again the catalytic cycle starts. So, as I have shown in the mechanism, so you see that protein structure carbonic anhydrase in the resting state. You see that the huge proteins which are wrapping this complex, and as you can see that at the middle zinc is sitting over here, and this is the water, this is the 3-histidine. Here I have removed all these proteins. So, you can see this inorganic molecules coordination complex, the zinc is sitting over here ligated with 3-histidine and water. When carbon dioxide comes inside the protein, you see that excess structure is shown over here. This is the carbon dioxide and this is they are coming close, and then there will be nucleophilic attack which converts carbon dioxide to a bicarbonate. You also can see that the zinc is ligated with the bicarbonate, the excess structure is shown over here, and if you remove this protein you can see the structure. As you can see that this bicarbonate will be released and gives rise to the resting state of the enzyme, and another catalytic cycle starts. I now will talk about another hydrolytic metalloenzyme, urease. What urease is doing? It hydrolyzes the urea into carbon dioxide and ammonia, and the rate of the reaction is approximately 10 to the power 14 times faster than the non catalyzed reaction. Now, this urease is an enzyme of great historical importance. It was the first enzyme ever crystallized in 1926. The crystallization of urease isolated from jack bean seeds was done by James B. Sumner in 1926. The discovery was laureated the Nobel Prize in Chemistry in 1946. Finding nickel in urease active site was the first indication of the biological role for nickel. The active site structure of this nickel containing urease enzyme is shown over here. As you can see that both the nickel center is ligated to histidine and one water molecule, and there is a bridging OH group which is actually bridge between two nickel center, and the distance between two nickel is around 3.5 angstrom. Now, I am showing here the excess structure of urease is shown over here. As you can see that a huge amount of protein is surrounded around this metal center, and once you remove this protein, you see that the inorganic molecules which is a dinickel center and which is bridged by a hydroxo group. It can be hydroxo or water bridged between two nickel center. I will now discuss about the mechanistic action of this urease enzyme. So, as I have shown that this is dinickel center over here, and then urea coordinates to one of these nickel through this carbonyl group, and then it increases the electrophilicity of this oxo group, so that this hydroxo of the other nickel center attack at this carbon, and after that it releases one molecule of ammonia and then subsequently after hydrolysis releases another molecule of ammonia and carbon dioxide. Then this catalyst urease is regenerated, which again starts the cycle. So, this is the way this urease enzyme works. So, in this lecture we have discussed so far the importance of metal ions in biological system. Metal ion concentration must be maintained within certain range within the cell, otherwise it causes various disease in our daily life. We also discussed today the role of non-redox active metal ions in particular. We have seen why nature has selected mostly zinc ion in the various metalloenzymes that catalyze hydrolytic and related reaction. The metal acts mainly as a Lewis acid and also does not change its oxidation state. In this regard, we also have discussed mechanistic action of two hydrolytic enzymes, namely carbonic anhydrase and urease. In my next lecture, however, I will discuss the utilization of redox active metal ions in biological system. Thank you.